Welcome to MEI Mechanics. We're on the topic Mechanics Basic Principles, and this is video 1.6, Resolving Forces. So the idea with resolving forces is that any force which has a size and a direction, and the direction can be defined by an angle, um, it can be split into two separate forces which are perpendicular to each other. Um, Often that will be horizontal and vertical, but it doesn't have to be. In this case, it is. So this force here, we can think of this as being two separate forces added together, one which is acting horizontally and one which is acting vertically. And when we resolve the forces, essentially what we're doing is we're working out what these components are, what the sizes are of these two separate forces which would add together to make the overall force. Now, in order to do that, we're going to use trigonometry. So if you think about basic trigonometry, we have three sides in this right angle triangle. This side here is the opposite side. This side is the adjacent side to this angle theta. And F is the hypotenuse. So if I write down, for example, one of my basic trig equations related to this triangle, I know that sine theta is going to be, well, let's say if I call this y, then that would be y over f. Okay, opposite over hypotenuse, and I would rearrange that then to say that y is equal to f sine theta. Okay, and it's this form which is probably the way that we're going to want to think about it. So rather than labeling that with a y now, I can just label that as f sine theta. And if I apply the same idea to this one, that would be f cos theta. And those are the sizes of those two components that make up the force. So the horizontal component is f cos theta, and the vertical component is f sine theta. So let's look at a few very simple examples of this, resolving a force. So here in this case, we've got a picture very similar to what we had before. It's just we have specific numbers on here now. So we've got a force of 40 newtons with an angle of 25 degrees to the horizontal. And if you remember, the horizontal component is going to be f cos theta, so that's 40 times cos 25, and the vertical component is 40 times sine 25. And then we just stick those into our calculator if we want to and get those numbers out. So that 40 cos 25 degrees is 36.3 newtons. That's to one decimal place. And 40 sine 25 degrees is 16.9 newtons to one decimal place. Now, I didn't necessarily have to do that final step. Often you may just leave things written involving a trig function. If it's the final answer to a question, then you'll probably stick it in the calculator and get a number out and write it to a sensible number of decimal places. But in terms of working out, or if you want them to remain exact, then you can just leave it in terms of the trig functions. A bit of a trick one here. You might just want to pause for a moment to think about this. What are the horizontal and vertical components of that? And so of course we might decide that we want to always think about horizontal and vertical components, but if the force itself is already vertical, as it is in this case, then the horizontal component is 0. So that's fairly straightforward, but it's important to point that out. Now of course the forces aren't always going to be going upwards and to the right, so we might need to think about making sure that we get the right direction in a sort of positive or negative sense in the horizontal and vertical directions when we're resolving these components. So if you try to draw a triangle with positive sides, essentially, then from your diagram you can establish what the direction is. Okay, so that one is obviously going to the right and down in some sense, so those components must be as they are in that diagram. So again, applying the basic trig, we'd find that the horizontal component is 40 sine 70 to the right, the vertical component is 40 cos 70 downwards. If you're writing that as a column vector, of course, then you'd have a positive number in the top value and a negative number in the bottom value, if assuming that we were defining up as being positive. It's worth pointing out here in this case that this angle that we were given is an angle between the force and the vertical, and so what that's meant is that the cosine has appeared in the vertical component and the sine has appeared in the horizontal component, which is different to how it was first. So don't assume it's always going to be sine with the vertical and cos with the horizontal. It depends on where the angle is that you're given. Okay, we could just as easily have been given something related to that angle here, which of course would be 20 degrees. So, you know, depending on where the angle is that you're given, you might be using different trig functions. So think carefully, go back to your SOHCAHTOA idea from your basic GCSEs whenever you need to. So similar in this case, so 35 degrees, the vertical component is the one which is adjacent to the angle, the horizontal is the one which is opposite the angle. So the trig function is going to be that way round. So cos is always with the adjacent, sine is always with the opposite. This sort of thing might occur from time to time, so you might need to do a little bit of basic angle reasoning before you can start. It's sensible, I would suggest, to always try to get this into a triangle, a right angle triangle. So we'll form a triangle here, and then we'll look at this angle, which we can work out because they have to add to 180. You can see that that angle there must be 50 degrees, like that. Okay. So now we're going to look at an example involving some actual mechanics and some Newton's laws. So imagine we've got a 25 kilogram box. It's being pulled by a 40 Newton force, but that force is acting at 30 degrees to the surface here, like that. Okay. So at some point we're going to need to think about resolving that force into its horizontal and vertical components. And we're told that the acceleration of the box along that surface is 0.1 meters per second squared. So we should have enough information here to work out the frictional and the reaction forces that are acting. Okay, so let's see, what can we do? There's a few things that we need to do. They don't have to be done in any particular order yet, but why don't we start by resolving this force into its components. So obviously it will have a horizontal component and a vertical component, and the horizontal component, because that is adjacent to the 30 degrees, that's going to be 40 cos 30 degrees, and the vertical component will be 40 sine 30 degrees. Alright, so we can think of these now as two separate forces, and we can then consider these alongside the other forces that we know are going to be acting. Another force that we know for definite will be acting on the block, of course, is its weight, and the weight, of course, is mg. We know the mass is 25 kilograms, so that weight is 25 g, and there's going to be a normal reaction force of r. Now we don't know what that is yet, but we will be able to work it out in a moment. And there's one other force acting. We're told it's a rough surface, that's one clue, and also we're asked to find the frictional force. So both those things are telling us that there's going to be friction involved. Because the block is accelerating in the positive direction, we can see that because of the force, the direction of that force. So the right is positive. That means that any frictional forces will be acting to oppose that. So the friction must be going to the left, and we'll call that force F. So we've got vertical things happening and horizontal things happening, and because we've resolved that force, those things are now essentially completely separate. So we can do two separate pieces of work now. We can work in the vertical direction and we can work in the horizontal direction, and we can apply Newton's laws. Now, because this thing is sliding along the surface, it has no motion in the vertical direction. So as far as the vertical motion is concerned, it is at rest and it's not accelerating in the vertical direction. So that means that the total force, by Newton's first law, the total force in the vertical direction must be zero. So if I add together the forces in the vertical direction, being careful to think about the signs, I'll say that R, so that's upwards, so that's positive R, and I've also got this 40 sine 30 here, so R plus 40 sine 30, and then I've got this negative force effectively here, 25G. All that together must equal 0. So I can rearrange that to find R, so I can see that R is going to be 25G minus 40 sine 30 degrees. And in a moment we will work that out, but we've got everything there that we need, because we know that G is 9.8, and we can use our calculator to get sine 30. Or in fact, if you know your trig functions, you know that sine 30 is a half. Now in the horizontal direction we have two forces acting. We've got the 40 cos 30 acting to the right, minus the frictional force F, because F is acting to the left. So we've got 40 cos 30 minus F. That, well, we need to be careful here, because this thing is not at rest, is it? It's accelerating to the right. So we need to use Newton's second law there, which is, tells us that the overall force is mass times the acceleration. So this is our force on the left. On the right, I've got the mass of the block, which is 25, times the acceleration, which is 0.1. So again, from there, it's just a case of rearranging. That will tell us that the frictional force is 40 cos 30 minus 2.5. And again, at that point, I might get out my calculator and work that out. Okay, so here is that summarized then. So these are the two equations that we wrote down before, and by doing that rearrangement that we saw, put those numbers in the calculator, we get these results. So we get R is 225 newtons, F is 32.1 newtons. Now here's another example. This is one where we're going to have to think carefully about, or make a decision really about how to resolve the forces. It's a similar situation in some ways to before. However, we've got a surface here which is not horizontal, and usually in situations like this, it is actually easiest if we then, rather than working in horizontal and vertical components, we work in components which are parallel and perpendicular to the surface. But we need to be careful then, because in that case it's going to be things like the weight of the block which is now going to need to be resolved, as well as in this case a force which is at an angle to the slope. Okay, so let's well, we're going to need to add a couple of things to this diagram to begin with. So firstly, we've got a 20 Newton force at 30 degrees to the slope. So let's put that on, and that is 30 degrees to the slope, like that. And that's a 20 Newton force. And the other thing that we have, of course, is the weight. If it's a 6 kilogram block, then that is going to be 6G, acting vertically downwards. But we're going to need to resolve that into two components. So we've got a component which is perpendicular to the surface and a component which is parallel to the surface and is acting in the opposite direction to this force. Now we've got an angle here of 10 degrees, and if we think about it, that angle there is the same as that angle there, so I've got an angle of 10 degrees inside there, which means that this component will be 6g cos 10 degrees, and this component here will be 6g sine 10 degrees. We're also going to want to resolve this force here, so that will have a parallel component of 20 cos 30 degrees and a perpendicular component of 20 sine 30 degrees. And we're being asked to work out just the frictional force. Okay, so there will be, and just for completeness, we will include the normal reaction force. Now we need to be careful. Normal reaction force doesn't always act horizontal, doesn't always act vertically. It always acts normal to the surface. That means perpendicular to the surface. So we'll put that in there, but because we're not being asked to calculate it, we won't say any more about that one. And the friction, of course, because the force which is acting is pulling the block up, and we're told that the acceleration is positive. Okay, so you need to be careful here, because you could have a situation where there was still a force pulling the block up, but because it may not be big enough to overcome the component from the weight, and it may be that the block would be accelerating downwards in some situations like this. But because we're told the acceleration is positive, then we're fine here, and so the friction must be acting that way. So again, let's apply Newton's second law. So let's write down all the forces acting in the positive parallel direction here. And so that is positive 20 cos 30 degrees. And then the other two components which are acting in the negative direction are this component of the weight, so we'll put that in as minus 6g sine 10 degrees, and of course we've got minus f. And remember, this is Newton's second law. We've got F on the left, on the right we have MA. So we have 6, that's the mass, times the acceleration, which we're told is 0.4. So we can rearrange that now for F. And there it is. Alright, so F is 4.71 newtons. So that concludes video 1.6 on resolving forces. The final video in this topic will be video 1.7, equilibrium of forces.